hold a smartphone, and you are holding the most refined silicon on Earth. The chip inside it is a crystal so clean that, in the best of it, fewer than one atom in a billion is a stranger. That is purer than almost anything our species has ever made. Silicon runs the modern world, and it is not rare. It is the second most common element in the ground under your feet, beaten only by oxygen sitting in the sand and the rock and the glass, and it has been sitting there for the whole of human history. Here's the part that should stop you. For almost all of that history, nobody could use the element at all. It was named after a stone. And as a pure substance, once we finally had it, it did nothing. Let me be careful straight away, because this is exactly the kind of story that goes wrong when someone gets excited. The compounds of silicon were never useless. They might be the most useful family of materials our species has ever touched. Flint is silicon, sand is silicon, glass, quartz, clay, brick, cement, the grinding stone, the window pane. All of it is silicon bonded to oxygen, the mineral called silica, and a great deal of civilization was built out of that stuff. So when people say silicon was almost useless, they cannot honestly mean the mineral. What was useless for thousands of years was the element on its own. Pure silicon, separated from the oxygen it clings to, the gray, brittle, faintly metallic solid that a computer chip is eventually carved from. That version of silicon had no job. For most of history, nobody could even make it. And on the day someone finally did, nobody had the faintest idea what it was for. Start where the human story starts, with a rock in a hand. The oldest stone tools yet found come from a dry riverbed at Lomekwi in Kenya, and they are about 3.3 million years old. The archaeologist Sonia Harman and her team reported them in 2015, and they pushed the tool-making record back so far that the toolmaker could not have been one of us. It was not our genus. It may have been an Australopithecine. That part is genuinely uncertain, and honest researchers say so. Those first tools, as it happens, were basalt, a dark volcanic rock, not silica. But watch what happens as knapping matures. The stoneworkers who came after, across 1,000,000 years and more, kept reaching for the same handful of materials: flint, chert, obsidian, quartz, and every one of those is silica, silicon locked to oxygen, the very substance the element hides inside. There was a reason for the preference, and it was not decoration. Silica breaks in a particular way. Strike it right, and it fractures in smooth, curved, predictable sheets, so you can shape an edge you could shave with. That clean fracture is a property of how silicon and oxygen pack together. The whole of the later Stone Age, the hand axes and the blades and the arrowheads, is a long argument with a single element about how it likes to break. So the element was quite literally in our hands from the beginning. We just met it as a stone. Then we melted it. Somewhere in the ancient Near East, people learned that the right sand, heated hard enough with the right additives, turns into something clear and hard and new. The oldest glass objects that survive come from Mesopotamia and Egypt, from roughly the middle of the second millennium BC, around 1500 BC and after. The Egyptians had been glazing crushed quartz into bright blue faience even earlier than that. A first cautious taming of the same mineral. Beads first, then small vessels, then, much later, windows. Glass is silica again, melted and frozen into disorder instead of crystal. Picture the workshop, a furnace roaring past the point where sand slumps and flows, a worker winding a glowing thread of molten silica onto a rod, the first people in history to make a solid you could see straight through. They had no idea what silicon was. They were reshaping it anyway. I want to hold on to that because it sharpens the whole puzzle. By the time of the Romans, silicon in the form of silica was doing enormous work. Glass, mosaic, mortar, pottery, the abrasive on a grinding wheel. And still, the element itself, the pure gray solid, was completely unknown. Nobody suspected it was there. Sand was just sand. The suspicion came late and from chemistry. In 1787, The French chemist Antoine Lavoisier looked at quartz and guessed that it was not an element, but a compound, the oxide of some new substance no one had yet pulled loose. He was right, and he could not do it. The bond between silicon and oxygen is stubborn, and his methods were not strong enough to break it. There is an irony worth naming, and it runs against instinct. Silicon was so hard to pull loose precisely because it is so common. It is common because it grips oxygen so tightly, and that same tight grip is what defeated the chemists trying to tear the two apart. The abundance and the difficulty were the same fact wearing two faces. A generation later, in 1808, Humphrey Davy tried and also failed, though he got far enough to give the thing a name from silex, the Latin word for flint. Even the name admits defeat by the stone. In 1811, two more chemists made a dirty, impure version and did not realize what they had. The clean result took until the early 1820s. The Swedish chemist Jans Jacob Berzelius is usually credited with first isolating silicon as a pure element in 1824, though you will see 1823 in some sources. And he did it by heating a silicon compound with potassium and washing the product. That was the moment. After 3 million years of holding silica, a human being finally held the element by itself. And here is the anticlimax at the center of this entire story. It changed nothing. A pure crystalline form would not even arrive until 1854. What Berzelius had was a brown powder that answered a question about the periodic table and almost nothing else. It was not stronger than iron. It was not prettier than gold. You could not build with it or forge it or trade it. The most abundant workable element on Earth held pure at last, sat on a laboratory shelf as a curiosity. That is not a figure of speech. For more than 100 years after it was isolated, elemental silicon had no important use. None. When a real industrial job for the element did arrive, much later, it was a humble one, with nothing to do with computing. Foundries learned to stir a little silicon into iron and steel, to clean the metal as it cooled, and to give certain steels better magnetic behavior. Honest, useful work. Still not the job silicon is now famous for. The element kept finding employment everywhere, except the one place it would eventually rule. So the paradox is laid out plainly. The element was everywhere. It was in every tool, every window, every wall. It had been named, isolated, cataloged, and it was still, as itself, good for essentially nothing. If a material is that common and that inert, the obvious conclusion is that it simply is not very useful. That conclusion held for over a century. It was wrong. The problem was never the element. The problem was that the one thing silicon is extraordinary at is a thing no one before the 20th century could see, measure, or control. Which brings the real question into focus. Not why silicon was useless, but why it stopped being useless exactly when it did, and not a moment before. The answer is two locks, and both had to open. The first lock was purity. Silicon is generous with its talents only when it is almost perfectly clean, far cleaner than a hand axe or a window pane ever needed to be. A few stray atoms of the wrong element and its behavior changes completely. For most of history, nobody could make anything that pure. And silicon in particular fought back because it melts at more than 1400 degrees and attacks most of the containers you would try to melt it in. The second lock was control. Even perfectly pure silicon does not do much on its own. Its magic only appears when you add a trace of another element on purpose. A whisper of boron or phosphorus, a few atoms in a million, in a process now called doping. That deliberate contamination is what turns silicon into a semiconductor, a material that conducts electricity only when and how you tell it to. The mechanism is simpler than it sounds. Slip in an atom of phosphorus and it brings a spare electron the crystal does not need, free to wander and carry current. Slip in an atom of boron and it leaves a gap where an electron should be, a hole that drifts the other way. Lay a patch of the first kind against a patch of the second, and the boundary between them behaves like a one-way gate for electricity. Stack those gates by the million, and you have logic. You have memory. You have, eventually, everything. Neither lock could open until we understood what was happening inside the crystal at the level of single electrons. That understanding is quantum physics, and it did not exist. The element had been waiting in plain sight for a science that had not been invented. This is the pattern the channel keeps running into. The idea was never the bottleneck. The kindling was missing. The kindling arrived in a rush in the middle of the 20th century. In December 1947, at Bell Labs in the United States, three physicists, John Bardeen, Walter Brattain, and William Shockley, built the first working transistor, a tiny switch and amplifier with no moving parts and no hot filament. Before it, the work of switching and amplifying a signal fell to the vacuum tube, a fragile glass bulb that ran hot, burned out like a lamp, and drank power. The first electronic computers held thousands of those tubes, filled whole rooms, and failed almost constantly as the bulbs died one by one. A solid sliver of crystal that did the same work, cold and small and durable, was the seed of every computer that followed. And here is a detail almost everyone forgets. That first transistor was not made of silicon. It was made of germanium, silicon's neighbor on the periodic table. For about the first 6 years of the transistor age, germanium won. It was easier. It melted lower. It was simpler to purify with the tools of the day, and the early devices worked. This is worth saying clearly, because it is where honesty matters. Germanium was genuinely the better choice at the start. Silicon was the harder material by every practical measure. If you had bet on merit alone in 1948, you would have bet on germanium, and you would have been right for a while. But germanium had a ceiling. It leaked current badly, and it stopped working once things got warm, above roughly 70 degrees, which is hopeless for anything rugged. Silicon, if only you could tame it, ran far hotter and leaked far less. And it had one more quiet advantage that turned out to decide everything. When silicon meets air, it grows its own skin of silica, a stable, insulating oxide, the same tough mineral in play since the Stone Age. That built-in insulator is what would later make it possible to print millions of components onto a single sliver. Germanium has no equivalent, so the axis that actually chose the winner was never raw ease. It was purity, temperature, abundance, and that oxide skin. On ease, germanium won. On the axis that mattered, silicon did. Taming it took two breakthroughs, and both were about the locks. In 1952, a Bell Labs chemist named William Fan published the principles of zone refining, a way of sweeping impurities along a bar of materials by melting it a slice at a time, over and over, until the dirt collects at one end and the rest is astonishingly clean. One later description put the purity at something like a single wrong atom in 10 billion. I have seen that compared to 1 grain of salt in a railroad car full of sugar, and the comparison is about right. Vaughn's method did not quite work for silicon at first because silicon runs too hot and too reactive, so a colleague developed a modified version a few years later that held the molten zone in mid-air, touching nothing. The first lock was open, then doping opened the second, and in 1954, at Texas Instruments in Dallas, Gordon Teal put the two together and built silicon transistors that worked. The scene is a good one. At an engineering conference that year, speaker after speaker stood up and explained that a practical silicon transistor was still years away, maybe a decade. Then Teal rose, and near the end of his talk, he said that, contrary to what his colleagues had been telling everyone, he happened to have a few silicon transistors right there in his pocket. He did. He pulled them out. The room understood in an instant that the future had just changed hands and changed materials. I should add a caution here, because credit for this is genuinely tangled. A Bell Labs chemist had made a working silicon transistor a few months earlier, but the labs did not chase it commercially, which left the public breakthrough to Teal and Texas Instruments. Who was truly first depends entirely on what you decide to count. I find the honest version more interesting than a clean one because it shows how many hands a single object passes through before we hang one name on it. From there, it accelerated. By 1958, Jack Kilby at Texas Instruments and soon after Robert Noyce at a rival firm worked out how to build many components into one integrated circuit on a single chip of silicon. The oxide skin made it possible. The whole digital age is downstream of that. It is worth seeing how far the taming had to go, because the modern version still begins where the Stone Age did. A chip starts as ordinary sand, quartz, silica, the same mineral a napper once chipped. It is smelted down to raw silicon, then purified through the long, molten sweep until it is cleaner than almost anything in nature. Then it is coaxed into a single continuous crystal, one flawless atomic lattice pulled slowly from the melt as a fat gray cylinder, which is sliced into the thin, round wafers the whole industry is printed on. Sand at one end, a mirror, bright disk of near perfect silicon at the other. Every wafer is a Stone Age material dragged to a purity the Stone Age could not have imagined a reason for. Now step back and see what actually happened, because the twist is not the one you would expect. Silicon did not beat some rival to become the heart of technology. Silicon never lost in the first place, because for its entire existence, the contest it would eventually dominate had not begun. The game that makes silicon priceless, the controlled steering of electrons through a near perfect crystal, did not exist as a game until the 1940s. You cannot lose a race that has not started. The element that would define the modern world spent millions of years in human hands doing every job except the one it is now famous for: blade, bead, bowl, window, wall. And the reason it waited was never a flaw in the silicon, it was a gap in us. We could not purify it, and we could not yet read the rules that governed a single electron inside it. The rock was always ready, we were not. And the pattern has not stopped. It is running again, right now. Silicon has carried computing for 70 years, and the scale it reached is hard to hold in the head. A single modern chip can pack tens of billions of those tiny gates onto a fingernail of silicon, each feature only a few nanometers across. A nanometer being a billionth of a meter, a span just a handful of atoms wide. That is the wall. The features are shrinking toward the size of individual atoms, and at that scale, the material starts to run out of room. Because you cannot make a reliable gate out of something only a few atoms thick. So the same argument is happening once more. There are other materials, silicon carbide, gallium nitride, and stranger ideas further out, each better than silicon on some particular axis, each held back for now by cost or scale or the plain fact that the whole world is built around silicon and switching is hard. Which of them wins and when, I genuinely do not know. And anyone who claims certainty is selling something. What I would bet on is the shape of it. The better material will not arrive when it is invented. It will arrive when the conditions that let us use it finally line up, exactly as silicons did. A hand axe from 500,000 years ago and the processor in a phone are, at bottom, the same element shaped by the same species. One was chipped for the edge it made when it broke. The other was purified past imagining for what a single electron does inside it. Between those two objects sits every year. We spent holding silicon without knowing what it could become. The rock never changed. We did.